thought you're from Florida. You go to the beach. All right, no class next week. We'll come back the following week. Okay, and the following week we have 4th of July, right? Wow, non-stop. Okay. Okay. All right, we'll do something simple today. We go back to the spectroscopy. Okay, just a small part of it, and are you all ready? You guys look sad. What's going on there? All right, say hi to people on Zoom, huh? Anyone want to say hi back? I don't know. When I talk to him, I look up on the sky. I have no idea why.
Hi.
Oh, okay. Oh, we gotta feel nice. Nice.
Hi.
Hi. All right, let's get started. Okay. Sit back and relax. So it's not that complicated. It's no compared to the whatever you learn in the past. Today it's like yeah. So it's not. It's quite fun to learn actually. Okay. All right. Let's start with this. Are you guys familiar with magnet? Okay, we'll do some cool experiment. Okay, if I have the a baseball put right in there, what would happen? No, it's not rocket science. No, nothing. No. Okay, let's try a bird. Anything happen there? Probably not. No. What died? Like what? What kind of bird? I don't know. Just a bird. Nothing happened. That's my point. Okay. All right. How about this? Anything happened? What? Which pole attract? Is it north and north or north and south? I mean the same pole, opposite pole. It's opposite. Nothing happened. No, nothing happened. Okay, but this, can you imagine what would happen? Okay, so the big magnet will force the little magnet to spin. Okay, so because north and south attract, like opposite pole attract. Okay, all right. So how that does it work? It's all about magnetic field. All right. Now, in a magnet, so the magnetic field go from north to south. Can we agree on that? Please do not go south to north. If you do that way, everything I'm going to talk about today just reverse. Okay. So go from north to south. All right. Okay. So this we call this magnetism. Or this is what you see like the line right there. I put line on there. Those are magnetic field. Okay. All right. Now, if you have a big magnet, so look right there. Okay. So I put the small magnet in between it, north and south. They attract. Everyone follow me? Okay. This is the compatible arrangement, alignment. Okay. Or the magnetic field aligned. All right. Now, if I so this is low energy. All right. If I use my my hand, force the little magnet to spin like that. Okay. Now look at the magnetic field. They repel one another. See that? Okay. So in this case, the one that have a larger magnetic field or one is stronger will force the little one to spin, go back to the compatible arrangement. Okay. All these are just we call it magnetism. Anyone familiar with this guy? What is his name? That's how they name it. Okay, this guy have an ability to create and control a magnetic field. One of the best ability, I think. Okay, okay. Besides the lady who can control the weather, what's her name? Yeah, some of you guys know it. Okay, all right. That's so this is magnetism. Read this real quick. Read. You done reading? Okay. All right. There are 3 atoms on here that do not have magnetism. I mean 2, not 3. 2 atoms do not have magnetism. Which one? One is carbon. Which carbon though? Carbon, which one does not have magnetism? Carbon 12 or carbon 13? Carbon 12. Okay, we look for like an even number. The even number does not have magnetism. What's the other one? Oxygen 16. Okay, so these two cannot be or they are NMR inactive. We cannot use them on NMR, but to come up with the NMR spectrum. Okay, so the common nuclei that are used in an NMR are proton. Okay, deuterium is not, because we don't have a lot of it. Does that make sense? Like in nature, not a lot of it. Okay, mostly the proton. Carbon 12, like highest abundant, but we can't read it, so we go with carbon 13. Okay, so C13, that's what we call it, right? Nitrogen, oxygen 17, fluorine 19 can be used in a proton NMR. I mean, a proton NMR instrument usually. Okay. All right. Anyone here is pre-med? Do we have any pre-med in the house? Okay. Answer this question. You familiar with that? MCAT question? Okay. Which one? C, good job. Have no magnetic moment. Like no magnet, basically. Okay. All right, next one I stole it from Khan Academy. Which one? We're down to these two, bottom two, right? What do you know about that? Hydrogen. What's the atomic number of hydrogen? 1. That's an odd number. So the answer is C, right there, neon. Okay. The difficult part is, how do you know the atomic number of that? If you know the rest. I mean, it just, yeah. So, anyway, okay. So only a specific nuclei can be used in an NMR. Okay, not all of them. We look for the one that have odd numbers. Okay, atomic number or mass number. All right, we're going to use that to explain the spin multiplicity. Okay, now we're going to focus on just a proton now. All right, just a proton. Okay, you guys are taking or have taken the lab. Which one do you guys use in the lab? This is the benchtop NMR instrument. Which one do we have? Is it the lab one? The lab one, right? Okay, so you have that one. Okay, the NMR spectra that you guys been reading with me or in the lab come from something like this. This is huge. I make it smaller, but this is really huge. Okay, so that's an actual instrument. All right, to explain the spin multiplicity, we're gonna start with the instrument. Okay, so there are a lot of process steps in here, and from the sample, from the compound all the way to the NMR spectrum, we're gonna talk about just like right here real quick. Okay, all right. So let's say you have a sample. Okay, so you put a sample holder, put it into the NMR instrument, whatever happened there. All right, we're gonna look inside. Let's see what we have in there. First thing first, do you see we have a magnet? Is everyone seeing we have a magnet? Okay. Which one north? Which one south? North to south. From that right there, over there, all the way to south. Okay. So there's a magnet. So the sample is under magnet. This is your sample in the test tube, whatever. Okay. It's under magnetic field, basically. All right. Now, what else we have? Okay, we have this guy right here. RF stands for radio frequency. In IR, we use IR. Remember that? Okay, we have UV, we use UV. NMR, we use radio wave. All right, so we're gonna pulse radio wave of about 16 times. Okay, so how does this work? What happened to the nuclei? Well, let's take a look. We're gonna take only one proton, just one proton. But you can imagine in a sample there are tons of proton. Can you imagine that? In a molecule, how many molecules are there? Each one have tons of them. And you have like a Avogadro's number of molecules. There's a lot of them. We'll take just one. Okay, so this is under magnet, all right? North right there, south right there. All right, so north to south, from bottom to the top. Okay, under magnetic field, charged particle moves. What are charged particle around the nucleus? Answer the question, please. What is charged particle around the nucleus? Electrons. Under magnetic field, charged particle move like that. That's a charged particle move. That's electron moves. Okay, and you create its own magnet. Look like that. North to south, from top to the bottom. All of them work like that. All right. Now, to draw like this, it takes a whole up space. So instead of I draw north to south like a show magnetic field like that, I'm gonna use just that arrow. Can we do that? Which one's the north? The top and the bottom, north. Which one north? The top. Okay, this is north. This is south. Okay, so we're gonna use the arrow. That's the north. All right. Let's do. I'm gonna start adding more nuclei. Okay, so let's say these are all protons. Okay, they're just like arrange itself arbitrarily. All right. Now we're gonna put this is sample in the NMR instrument, and under NMR instrument, what do we have in there again? What do we have in there? We have a magnet. Okay. All right. We're gonna put under magnet. What would happen when you put all this guy under magnet? They will arrange itself like that. Do you guys know why? Like, how does it go from here? Like this is, everyone can just point anywhere, any direction. When you put this under magnet, everyone just arrange itself like that. North to south. How come? Explain this to me. Which one comfortable? The left one's comfortable, right? When you make it uncomfortable, what happened to it? It gets flipped. It gets the big magnet force the little magnet to go to the comfortable arrangement. Does that make sense? Same thing there. Because we have a big magnet from the instrument, and everyone behave like a small magnet. Okay, everyone follow me so far? It's a bunch of cartoon. All right, next one. Besides magnet, NMR use radio frequency. We're gonna pulse it with radio frequency. Watch closely. 1, 2, and 3. Pulse. Some of this will absorb energy, but it's very small energy. It's even smaller than IR, than infrared. Okay. What does it do? Well, this guy gets flipped. That's all it does. Change spin state. Okay, so I'm gonna put the spin state on here so we can communicate. So we have the one that stay, we call alpha, and we have the one got flipped is beta. Okay, which spin state under magnet is more stable, alpha or beta? And alpha. Okay, why beta is uncomfortable? Why? Does that make sense? That picture tell you, okay, beta is uncomfortable, it's unstable, all right, it's high energy, basically, all right? So when things uncomfortable, it release energy and relax back to alpha. Watch, okay? The beta one, look for the beta one, okay? So right now it's uncomfortable, this guy release energy, and then this guy relax back to an alpha spin state, okay? That's more comfortable, all right? So basically, the radio wave is like our hand, we just go spin it. Does that make sense? We do one more time. Like 1, 2, and 3. Pulse one more time. Some of this was flipped to a beta spin state. Is it comfortable? Nope. Relax back to an alpha spin state and also releases energy. Okay. Going back from beta to alpha releases energy. That energy can be detected and translated to a proton NMR spectrum or carbon NMR spectrum. This is how the roughly how the NMR instrument works. Go from beta to alpha. Okay. All right. Only some certain type of nuclei can do this. Not all of them can. The one that have magnet can. Okay. All right. Let's talk about spin multiplicity. Okay. All right. HA by say we will focus on HA. All right. So HA under magnet. Okay. HA is a nuclei, just like one little ball you saw earlier. That's just one. Okay. All right, under magnet, what happened? Well, you pulse it. HA can be either alpha and beta spin state. Everyone follow me? Okay. Going from beta back to alpha releases energy. That energy can be detected. You get a signal called singlet. Okay. Now, when does HA show spin multiplicity? Like doublet, triplet, quartet. When does it show spin multiplicity? It got neighbors, right? All right, I'm gonna put one neighbor, just one neighbor next to it. Okay. All right, so right now we have HA and HB. Okay, both can behave as magnet. All right, under magnetic field from north to south. Okay. All right. So pulse it. Both HA and HB can be both alpha and beta spin state. Everyone follow me? Okay. We're gonna look at how HB affects HA. Okay. We're gonna look at how HB affects HA. Are you ready? Are you ready? Watch. HB can be both alpha and beta. Look at alpha HB first. This is alpha HB, okay? This is the magnet. Everyone look at HB real quick. What is the direction of magnetic field of HB? Can you tell me? There's a point right there, that's a north. What's the direction of HB? Go north to south. Are you following me on that? You go from north to south, right? North is at the top, so look like that. Does the magnet of HB make sense to you? North to south, okay? Now, I would like you to see, look at HA. If you stand on HA right now, imagine yourself stand on HA. You will feel two magnetic fields. One is the external magnet. Two is the magnet from HB. Everyone follow me on that? You might be familiar with the anisotropic effect, same concept there, okay? If you stand on HA, you will feel two magnets. One is from external magnet from instrument, from north to south, okay? North at the bottom. And the other magnetic field come from HB, north right there to south. I would like you to look at the direction of the magnet from the instrument and HB. Look at the direction of magnet from HB and instrument. Do they align, or do they go the same direction or go against one another? I'll say one more time. You got to listen to me carefully. Imagine you stand on HA. Imagine you stand on HA. You feel two magnets. Everyone follow me. Okay? Now, look at the two magnets that you feel. One is from the instrument, north at the bottom, south at the top. The other magnet from HB, north right there, go to south right there. Do these two magnets go the same direction or go against one another? Against one another. Can you see that? So when you see this, we can say that, hey, HB actually shields HA from the external magnet. Okay? If you stand at where HA right now, HB actually shields you from the external magnet. Guess, this is alpha spin state. What would happen to beta spin state of HB? What does it do? It's the opposite. Does that make sense? Okay, we're going to go there in a bit. Okay, let's go back to right here. So HA is being shielded by HB. Okay, shield from the external magnet. Here's the original signal of HA. When the nuclei is shielded, does it go to the left side of the spectrum or does it go to the right side of the spectrum? The right side. So instead of this signal right there, you're gonna get that. Okay. All right. This is HB alpha spin state of HB. Let's try beta spin state of HB. Look at the magnet. North right there, north going down now to that, and south going to the top. Okay. You can see that the two magnets from external magnet, north at the bottom, south at the top. And the magnet from HB, they go the same direction. Can you see that? So in this case, we say that HB de-shields HA. And de-shielding, what would happen to the signal? Go downfield or go upfield? Go downfield, you get another one. That's a doublet. 50% of HA being shielded by HB, and the other 50 is being shielded by HA. So you have a doublet, 50-50, like almost equal height 1-to-1 ratio. Yeah, that's a doublet. Okay. All right, hold on. Let's try one more time. Let's try. I'm going to add another nuclei. So we have two HBs now. Okay. And yes, when you pulse it, both HBs can affect HA by either shielding or de-shielding HA. Does that make sense? Okay. What are the possibilities here? What are the possibilities? The first one on the far right here, this is upfield one. Both HB shield HA. Does that make sense? Okay, that's one possibility. Give me three more. There are four total. What are possibilities? One shield, one de-shield. Okay, so one shield, one de-shield, one shield, one de-shield. Those are the two. This one, the signal stay the same, doesn't move. All right, and what's the last one right there? The de-shield one. Both are de-shield, shift to downfield. Okay, if you do the math right here, it's 25% each. It's a chance. Right, it's go by chance. Okay, the probability. So 25%. This is 50% total in the middle. Now what we have from HA by itself gets split. into 1 to 2 to 1 ratio. We call this a triplet. You know? It's about magnets, the direction of magnetic field. All right. All right, one more time. So now we have 3 HBs. Okay, we know there's a quartet, right? 3 HB now. So put under magnet, okay, and then we pause it. Here, so we pause right there. All these HB can be either alpha and beta spin state. Okay, what are the probability? What are the chance? What's the first one right here? Shielded one. All shields. Okay. Next one. So next one gonna be 2 shields. The 2 shield, 1D shield. The next one gonna be 1 shield, 2D shield, and the last one is what? All D shields. Each one is about 12.25% each. 1 to 3 to 1 ratio. Can you all see that? Okay, this is the quartet. Like that. Yeah, that's why we have n+1 rule or whatever. It's all come from the magnetism. Okay. All right. If you were really good at math, okay, anyone like love calculus, algebra, you can explain. It's another way to explain. There's multiple ways. Using have you heard the term Pascal triangle? Okay, you can explain like that too. I'm gonna show you how to. Okay, so all right, no neighbor, you get a singlet. That one neighbor, a doublet, you all know that. Okay, triplet, quartet, and go from there. Okay, so this is a Pascal triangle, look like that. These are things add on to one another. Let me explain this way. Okay, all right, HA by itself is singlet. Everyone follow me? It's a singlet. Okay, once you have HB next to it, look what happened. Okay, half of HB alpha spin state, the other half is beta spin state. So you get this guy gets split into a 1-to-1 ratio. All right. Now next one, put second HB onto it. This HB will split each one of this one more time. Because this HB can be alpha and beta. This guy gets split. Okay. When it's split, look what happened. The middle one, their 2 signals add up to. Okay, so that's why it looks like this 1, 1, 1, 1. The middle becomes a 2, 1 to 2 to 1. Okay. All right, next one. Adding one more HB right there. Each one of these gets split one more time. Okay, gets split one more time. Take a look right there. Can you see the overlap right there? Okay. From 1 to 2 to 1, this is 1 and 1 and 2. 1 and 2, you get 3. 2 and 1, you get 3. And 1 and 1, you get 1. 1 to 3, 3 to 1. That one. That's a quartet. This is Pascal triangle. All right. So that's why we have this spin multiplicity. Does this make sense at all? All right, let's talk about what we are interested in. Okay, the things I've been talking about, you don't have to write down. Let's talk about what we're interested in. We're interested in, look at this doublet, the gap between multiplicity. That's what we're gonna learn today. Okay, we call this a J value or a coupling constant. Same terms. You can use either way, J value, coupling constant. Okay, so it's a gap between the 2 signals. All right. Now look right here. So we look at the ethyl group. Eyes on the ethyl group. There's a red, there's a green. Okay, so the red is the quartet, and the green is a triplet. When I explain with a coupling constant now. Okay, we talk about how or what causes spin multiplicity. All right, we already talked about that. We're gonna focus on the gap between each signal. I mean, each peak, not each signal, each peak. Okay. All right, look at just these two. I'm gonna put the name on it, HA and HB. Okay. So HB is a triplet, HA is a quartet. All right. Here's a coupling constant. Let me explain. All right. HA. Which one HA again? The quartet or triplet? One more time. Which one is the HA? Quartet or triplet? A quartet. Okay. Who makes HA a quartet? HB. Okay. So we say this: HB split HA split HA to a quartet. Right. That's why we have a quartet. The coupling constant or the distance. Okay. The distance right here between the peaks is about 7.2. They come from instrument. You don't need to know the number. You have to measure it like a chemical ship. You gotta measure it. Okay. Now 7.2. So the gap right there is 7.2. 7.2. Now let's look at the nomenclature real quick. JAB. Don't call them Jap. Do not. Okay. JAB. It means B split A. Does that make sense? Coupling constant of A split by B. JAB. Okay. All right. Next one. All right. Now, if B split A 7.2, guess what? HA also split HB 7.2 as well. JBA. Did not? A split B. Same number. Okay. So couple protons. Couple proton have the same coupling constant. Now, this might be sounds like memorization. Let me explain this way. This might be make more sense to you. Eyes up, guys. Eyes up. Hey, put your pen down. 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 Are you familiar with this toy? Am I too old? It's a millennial thing. So, what is it? What do we use walkie-talkie for? It's an older telephone. Does that make sense? All right. So, but allow us to talk for a certain distance. If I'm here, you out there, we can still talk, communicate, right? Now, let's say you have one walkie-talkie, I have one walkie-talkie. If you want to talk to another, talk onto the walkie-talkie, what do we have to adjust? The frequency. It's got to be the same frequency. Does that make sense? What's the unit of frequency? What do we use? What do we pulse on the nuclei in the instrument? Radio frequency. It's radio wave. So my point is a couple proton A and B. If B split A 7.2, A gotta split B the same number. It might be like 7.3. Right? You can adjust, let's say in walkie-talkie, if I'm going 7.2, you do 7.3, 7.4, 7.1, we might be able to talk still. It's close. Does that make sense? Okay? But it's gonna be darn close. You can do like 7 and 10. That's not, you can't communicate there. Okay? So my point is these two protons, they use walkie-talkie, they communicate to one another, they split one another. That's my point. All right? So a pair of couple protons, they have the same J value right there. Okay, couple protons have the same coupling constant or J value. It tells you that they are next to one another. We'll use that. I'll show you how to use that when you interpret the spectrum. Okay. Now we use a tree diagram. This is how we chemists communicate. Okay. How you explain spin multiplicity. All right. I'm going to show you A. I'm going to have you do B. If you look at the handout, I have like I give you grids. You see that? Like a bunch of lines. You're going to use that in a bit. I'm going to show you the first one and have you do the other one. Okay. Eyes up first. This is very easy. I mean, it really easy? But if you don't listen to it, you just lost. Okay. All right. Watch closely. All right. HA right here. One more time. What's the spin multiplicity of HA right now? Quartet. Who causes quartet of HA? HB. Okay. Here's what happened. All right. HA. Without HB, HA is supposed to be a singlet. Without HB, HA is a singlet. Does that make sense? I'm gonna draw one line like that. That's my singlet. Okay, hold on to it. It's not like regular singlet. Not yet. Okay. All right. If you have only one HB next to HA, what would spin multiplicity of HA be? Doublet. Good job. Okay. All right. So HB. If you have only one, there are 3 total. But we get there. Just one right there. HB will split HA. How far apart? 7.2. See that? So I'm going to put the ruler right there. You don't have a ruler, but I give you grids. Make sense? Okay. Hold on. Don't do anything yet. All right. So I'm going to, let's say about 7. Keep the easy number. Okay. I'm going to split this line to 7. So I'm going to do 3.5. 1, 2, 3.5 to the left. 1, 2, 3.5 to the right. That's about 7. 1 HB, you get two peaks. That's a doublet. Can you see that? How many HB do we have again? 3 total. We have to do 2 more. All right, next one. Second HB, split one of these 2. All right, so 1, 2, 3, 1, 2, 3.5 to the left. 1, 2, 3.5 to the right. One more time. The touch in the middle. That's a second HB. You get a triplet now. Now we have 3 HB total. So one more time, take another HB, split one more time. 1, 2, 3.5. 1, 2, 3.5. We have four peaks. That's a quartet. Now let's sketch. We're gonna sketch the spin multiplicity. You know it's a quartet, right? That's why I'm just showing you. Oh, don't do anything yet. Let me show you. I'm gonna have you do another one. All right. So let's sketch the spin multiplicity. Okay. Let's look at the intensity first. Eyes up top. HA by itself. That's which is one signal split into 1-to-1 ratio. The first split 1-to-1. Okay. Second split. Watch closely. This guy split to the left, split to the right. The other one split to the left, split to the right. You're gonna get 1 to 2 to 1. Does that make sense? Give me the ratio, the height ratio at the bottom. 1 to 3 to 3 to 1. That's a quartet. 7 hertz apart. You can sketch that easily, which is that. Can you do this with HB? Let's do with HB. HB is a triplet, is it not? HB is a triplet. All right, let's do HB. Okay. Eyes up, eyes up, eyes up. HB by itself is a singlet. Okay. Now, who caused spin multiplicity of HB, or who split HB? HA. Okay, we have 2 HA, so you do 2 times. All right. Let's start with HA. Now I'm gonna split HB. How far? About 7 hertz. Okay. HA split HB, HB split HA, same number. So when you do 3.5 to the left, 1, 2, 3.5, 1, 2, 3.5 to the right. That's the first HA. One more time, we have 2 HA total. One more time, so split one more time, so you get that 3 peaks. Okay. Let's do the height. The first split, you get 1-to-1 ratio. What's the ratio of the second split? 1 to 2 to 1. Okay, and that's the triplet. Can you see that tree diagram is not complicated? And you can explain even the complicated one. We're going to focus on the complicated one. This is simple spin multiplicity. We'll learn about complex spin multiplicity. It looks something like this. We're probably not going to go to the right one. That's nasty. Okay, we just go to the surface. The left one, doublet or triplet doublet, something like that. Okay. All right. Before we get to the complex spin multiplicity, let's talk about what causes complex spin multiplicity first, so you understand. All right. Put your pen down. Put your pen down. Just think right here. I want you to think with me. All right. Look at this nitropropane. Okay. We're gonna focus on HB. Answer the question. What's spin multiplicity of HB? The what? Sextet. Okay. So it's 1, 2, 3, 4, 5, 5 neighbors. Sextet. Okay. 6 peaks. All right. So who split HB? You can say that's a A, right? Was a split, so we have that 2 A's. We have 3 C's, and that's a coupling constant. Okay, so make HB a sextet. Take a look. It's a sextet. I'm gonna go quick right here. So B split by, you can do A first, you can do B first, doesn't matter. They have the same number. I'm gonna go do what? This one A. First A and the second A. Okay, Two A's make HB a triplet. Everyone follow me. Okay, we got two A's. Okay. Now, what else? We have three C's to go. Three HC's to go. Okay. All right. First C, second HC, and then third HC. That's a sextet. Can you see that? Okay. Well, let's do the high. We haven't talked about the high yet. Okay. Before we split them, we draw now. So get 1 to 1, 1 to 2 to 1. What's the next one? 1 3 3 1. Next one. 1 4 6 6 4 and 1. Okay. And the last one. This one. Well, you do the math. There's a 10 right there. There's a 10 right there. See that? So you get that. 5 and 10 about double the height. Yeah, that's how we sketch. You'll be sketched like this too on exam. Okay. All right. So we have HB right there. Sextet. 1 to 5 to 10 to 10 to 5 to 1 ratio. Now, complex spin multiplicity. Watch closely. Okay. All right. Right now, take a look right now. This is what we just did earlier. HB split by HA about 8 hertz apart. Okay. And HC also split HB about 8 hertz apart. What if? Think with me. What if these two 8 hertz are not the same 8 hertz? Not the same number. That's my point. One's 7, the other one's 8. Let me show you. Iodopropane. 6.8, 7.3. Not the same number. Is HB still a sextet? That's the question. Okay. All right, when these coupling constant are not the same number, let's watch. All right, we'll use a tree diagram to explain. Okay, so this one you're gonna be on scale right here. So first HB, I'm gonna split by HC first. Okay, how far H? So JBC 7.3, 7.3. That's about 7.3. All right. How many times I have to do this for HC? For HC, how many times? 3 times. That's a 1. Okay, that's a 2. That's a 3. That's a quartet. What else I have to do? 2 HAs. Make sense? 2 HA. Now, when I split this, it's not 7.3 anymore. It's only 6.8. Here's the first HA. Can you see what's gonna happen next? Second HA. I'm getting nasty there. See that? Now what we have? Still a sextet, but it's a little. Someone help me. How do you explain it? The what? It's sextet, but it's not like a nice sharp sextet. What's that? What? Okay, they got jacked at the top. See that? It's still kind of a sextet, but it's not as nice and sharp sextet anymore. All right. Now, can you imagine? Go back one slide. What if the two numbers are wildly different? Let's say 5 and 10, 5 hertz and 10 hertz. You're not gonna get sextet. You get something else. Okay, so that's what we call this complex spin multiplicity right here. Okay, they are a few. What we just learned right there. So the signal a little skewed. Okay, so yeah, we'll learn the alkene system. Alkene with the methyl group on alkyl group system. We have benzene or mix between benzene and alkene. Those are the systems that we'll learn. Not more on that. Okay, all right, we'll start with an alkene. The smallest system right here we look at is styrene, like a styrofoam cup. This is the monomer of it. Okay, so we're going to focus on HA, B, and C, the proton on an alkene. Okay, all right, we're going to focus on, so right there, 3 signals. We have HA, HB, HC. We're going to match them, put in there. But you can see in the signal right here, none of them look like simple multiplicity, like doublet, triplet, quartet. Can you see that though? It's not like that. Okay, we're gonna explain this way. All right, let's look at the coupling constant in an alkene system. All right, which pair of protons give you the largest coupling constant? Which one? What? Trans one. See that? You don't need to know the number. All you need to know is like a chart, like a cloth size, large, medium, and small. Can you do that? You don't need to know exact number, but if you want an exact number, I mean, you want to memorize the range, sure, be my guest, but you don't need to. Yeah, 12 to 18, the largest one, 6 to 12, about 3, yeah, okay. All right, we'll use this to explain, okay. Let's look at the HA. Let's look at HA. Who can couple or who can split HA in this system right now? HB and HC, okay? Now let's look at a coupling constant which come from the instrument. You can memorize it. Everyone have different number, like a chemical shift, okay? So HB split HA, 16.8 hertz. HC split HA, 10.2. Okay, and we also have B and C. This is geminal, right? Geminal right there, very small, 0 to 3. This one we found 2.4. Okay, those are the numbers we need. Now what? We start with HA. What's spin multiplicity of HA? Let me show you. Okay, so HA by itself is a singlet like that, just a singlet, one peak. All right. Now HB and C can split HA. You can do C first, you can do B first, doesn't matter. But we usually conventionally we usually do with the larger coupling constant first. Okay. All right. Let's do B first. JAB, which means B split A. Okay. So 16.8 hertz apart. So I'm gonna go 16.8, 17. What's the half of 17? What's the half of 17? 8.5. 1, 2, 3, 4, 5, 6, 7, 8.5. 1, 2, 3, 4, 5, 6, 7, 8.5. About 16.8 hertz. Okay. Now next one, HC also split HA, but only 10.2, about 10. 5 to the left, 5 to the right. Do you get that? Let's look at the height. The first split 1 to 1. What's the second split? What's the second split? Say 1, 1, 1, 1. No one touch. See that? No one touch. You get that. We call this a doublet by HB, doublet by HC. The spin multiplicity of HA is doublet of doublet. That's how we call it. Okay. All right. Which one is HA though? Which one signal of HA? You have to look at the coupling constant. I'm going to go back one slide. How far is coupling constant? You got two coupling constant now. We got 16.8 and 10.2. Remember I told you, think about the chart size. What does it mean to you? Medium, large, medium, or small? That's a large, medium, or small? That's about medium. Okay. Only A. Hold on. A. I'm gonna go back one slide. Right there. This is large. What does large mean? Large mean they're trans. Medium mean it's cis. And small mean geminal on the same carbon. Okay? So I'm gonna go back right here. It's a long back. Let's forward. All right. Look at the coupling constant. 16.8. What does it mean? Large. What does large mean in the on an alkene? Trans. So HA, it's only HA and B, they have trans. See that? Next one, 10.2. What does 10.2 mean to do? Large, medium, or small? Medium. What does medium mean structurally? Trans, cis, or geminal? Cis. Only HA have trans and cis. That's an HA. Coupling constant can identify directly which proton is which signal. Is that detailed? Okay, so that's an HA. All right, we're gonna practice this. I would like you to use to draw a tree diagram for HB. Look at the handout. You have a grid. Draw a tree diagram of HB. Yeah, 16.8 hertz. You can assume 17. Make an easier number. All right, who split HB? Well, HA split HB, HC, CCAT also split HB. Okay, I'll start with HA first. HA split HB. How far apart? 16.8, about 17. Okay, so 8.5 to the left, 8.5 to the right. Big split, big split. All right. Next one, which one? C split HB as well, but it's small, only 2.4. So one, let's say 2.4. That is about 2.4, a little bit over 1 each. Okay, small split. All right, now let's sketch. Okay, so the first split you get 1-to-1 ratio. The second split still 1-to-1 to 1-to-1 ratio. Nothing touch, nothing overlap. Okay, so you get that. What do we call spin multiplicity of HB in this case? So the first doublet and second doublet, so doublet of doublet still. They're all doublet of doublet here. Okay. All right, we're gonna match. Okay, so we have the sketch, the spin multiplicity now. Next one, we're gonna match to the spectrum. Which one is HB? Which one is HB? The one around, like say 5.7 or the 5.5? Which one? 5.5. Look at the coupling constant. Okay, if you don't know how to do this yet, 16.8. What does the size mean to you? Small, medium, large. Large. What does large mean? Trans. B has strength. That one. See that? Let's try one more time. 2.4. Small, medium, large. Small. What does small mean? Geminal. So we have B and C at geminal. So B right here, trans, half geminal. That's a B. And the other one is C. And C, same thing. Doublet of doublet too. And you see, if you look at the hand, handout, I give you the tree diagram of HC. Am I right? Same thing. I'm not gonna go over it. Okay. So, all right. Question about the coupling constant so far. Tree diagrams. Let's talk about how to use it. Okay. All right. Put your pen down. Now, I really want you to think, because you do this on your own on exam. Okay. Here's a thought process here. But I'm gonna walk you through it. All right. First thing first. What should you do? How about degree of unsaturation? This is formula, right? What's the DOU? 1. Good job. Okay, this is DOU of 1. It's not going. Okay, 1. Okay. Anything else on it? Look at IR. What do you know? It's sp2ch, sp3ch, maybe cc double bond 1625. Maybe. Still remember that? Must have been a long time ago. Okay, it's been a while. Listen carefully. Okay, now this one more important. DOU of 1, we might have a double bond. Let's check on the proton NMR. Do we actually have a double bond? How do you know? Can you see some of these are from the signal on a double bond, like vinylic protons? Which one though? A, B, C, D, and E. Which one are the protons on a double bond? Vinylic proton. Okay, let's do this. What's the typical range of an alkene? 5 to 6. Okay, about 5 to 6. So we have way above 6. This one quite lower than 5. Okay, but at least this guy, at the least. Are you following on that? Okay, so now let's look right here too. Look at the coupling constant, 17.5. What does it mean to you? This is trans, large number. This is trans. See that? Hold on. Put your pen down, guys. You gotta put your pen down. This is important. You try to keep writing things. 17.5 means trans. Anyone else has 17.5. Can you see that? That's the HC, which means that they're next to each other. They're gonna be on a double bond to one another. Does that make sense? Hold on. Look at 11. What does 11 mean to you? Small, medium, large. Let's say medium. What does medium mean structurally? Cis. Anyone else has medium? Has cis. D2. These guys are on the double bond. That's the logic, makes sense. Okay? All right, so let's do this. Next one, look at the integration. We're gonna jump around real quick, okay? But it's gonna be the drill. You'll get used to it. Look at the integration of these three signals, HA, C, and D. How many protons are on this double bond total? 3 total. What type of double bond is this? Tetra substitute alkene, tri-substitute alkene, disub, monosub, or unsubstitute alkene? This is monosub alkene. How's that? We start getting structure now. See that? Next one. All right, we're gonna look for where they are. We're gonna look for where they are now. Okay. Now let's start with the HA. All right. Let's start with the HA. HA have 17.5. That guy have 17.5. So A and B are trans to one another. Everyone follow me? A and B are trans to one another. So you got two options. These two. I mean A and C, not B. Sorry, A and C are trans to one another. You got two options. Which one? You need other information to help. The left one or the right one? If you say the left, why not the right? If you say the right, why not the left? Can you tell me why? Yep. So look at this other information. 11. What does 11 mean again structurally? Cis. 17 and a half, that's a trans, right? 11 is a cis. A has a cis. 2D. That's 11. If you put A right there, A wouldn't have cis. Can you see that? But if A right there, A is a cis. And cis to whom? Cis to D, that hydrogen right there, that's a D. Confirm it too. D and C, look at that, D and C are geminal. What do you know about coupling constant of geminal protons? Large, medium, or small? Small, check real quick. Hold on. 2.3, small. See that? Guys, look right here. If you know how to read coupling constant, you get exact location where each protons are. How amazing is that? In the larger structure, this helps so much when you're like not so sure where things are. Okay? All right, next one. This one probably easier now. All right, so we have B and E left. Okay, we have B and E left. Look at the coupling constant. B have a coupling constant 8.5. E have a coupling constant 8.5. Same number. What does that mean? They are next to each other. Everyone follow me? Same number, they're going to be next to each other. Okay, so B and C are next to each other. All right, so it looks something like that. And look at the spin multiplicity. Quartet, triplet, exactly. CH2 is a quartet. We got 3 neighbors. And E, CH3 is a triplet, 2 neighbors. They are next to each other. Okay. All right. What else? Look at the chemical shift. This guy really de-shielded above 4.5. Someone has to de-shield HB. Who? We have only oxygen. That's it. They're going to be oxygen. Put them together. This is monosub alkene. That's it. See that? All right, you're going to go practice that over the break. Something like this. Okay. All right, one last thing I have to explain on this spectrum. Okay, one more time. Answer this question. What is the typical chemical shift range of an alkene, proton on alkene? Guys, open your mouth. What's the chemical shift range? 5 to 6. All right, I'm going to explain like this. Watch closely. Look at HA. What's the chemical shift is 6.5. It's not in the range, like way de-shield, way downfield than the range. Explain to me why. Next to oxygen, inductive effect. Make sense? That's why it's go above. Okay, normally 5 to 6, this one 6.5. Next to oxygen, makes sense. All right. Now move to D and C. D and C is about 4. About 4. Way too shielded. Way too upfield for an alkene. How will you explain that? This is an ether, right? An oxygen right there. Oxygen is electron donating group. That's a hint. Can you explain how having electron donating group shield H, D, and C? What effect? What effect? Resonance effect. Watch. right there. See that? By a little, not a lot, by a little. Okay? By a little. All right. Now, we use coupling constant to construct the structure like this, you saw earlier, okay? We can also use coupling constant to distinguish closely related structure. For example, this one probably easier. They are stereoisomers. Can you see that? Same molecular formula, almost identical chemical shift. Okay, but you can see structurally the biggest difference is a cis and trans proton. Am I right? Okay, if I give you two spectra, proton NMR spectra, one from the left, the other one from trans, the other one from the cis, how would you distinguish them? Which one trans, which one cis? How do you know? We look at the coupling constant, right? All right, let's take a look at it. Okay, same thing. We have the small, medium, large. Okay, look for those. Look for those. Which one? Which one? Where? Okay, let's do this. Some people, like when I show this, some people got so confused. Where should your eyes be? Should your eyes be upfield? No, why not? It's some, you know, the answer. Tell other people why should your eye not be upfield? There's no double bond up right there. Where's the double bond region? Downfield 5 to 6. Your eye should be right there. Does that make sense? On the like 5 to 6 range, right? If you look at 5 to 6 range, you look at these two signals, 16.4. Which one? This is trans. Do you see how this works? Okay. All right. Do you know this reaction? Come on. Do you know this reaction? Have you learned it? Yeah, right? What do we call this reaction? It's a name reaction. Because of Wittig reaction. Okay? We make a double bond. Okay. So look at this ylide. Look at ylide. When I say ylide, you know which compound I'm talking about? The phosphorus one. Is it stabilized ylide or unstabilized ylide? Stabilized. It got electron withdrawing group next to it. This is stabilized ylide. Stabilized ylide gives you cis or trans? Stabilized ylide give you cis or trans? All right, I'll tell you right now. So you haven't studied yet. It's fine. It's cool. All right. So you got options. All right. One is cis. The other one is trans. Stabilized ylide give you trans. Okay. So should be the first product there. All right. Now this is the actual reaction. I made students at Tulane University as well as Indiana University do in the lab. They make this too. They do the reaction, recrystallize the crude product. Once you have a pure product, check melting point and then check NMR spectrum. Okay, we take NMR. This is the NMR that we got. What do we have? Here's this. This is this reaction. This is stabilized ylide. What do we have? Cis, trans. It's a trick question. What do we get? We get both. We have both. How do you know? Let's start with a 16.8. 16, oh, it's 16. That's a trans. Make sense? That's a trans, right? Now we have a little one right here, about 12 down here. That's a cis. We got both. But which one do we have more? Guess. The trans. We have more. We have more trans. Wittig reaction is selectively, not specifically, selectively produce cis and trans. Okay, this is stabilized ylide. You get trans. More trans. You get both, but you have more trans. It's a major product. Okay, so this student have to do even further. If this guy produces, can we agree on that? We have more trans than cis, right? This is trans 16 right there. There's a trans proton, there's a cis protons. See that? So we have more trans than cis. All right. Now, how much more trans do we have? This student have to go figure it out. This is how you do. Okay. Imagine this: if you have 50% each, that proton on the trans and the proton on the cis should have the same integration 1-to-1. Are you following? If we have 50-50, think with me. If you have 50 trans, 50% cis, the same proton should have 1-to-1 ratio integration. All right. So we use integration to tell how much more it one or the other. So this is what we do. Look at one of these. So let's say 16 hertz right there, integration of 1. Can you see that? It's that proton right there. It's that proton, or the other one, doesn't matter. Okay. Same proton right there. 12.8, 0.06. That's the same proton. How much more of this do we have over that? 1 over 0.06 times 100. That's a percentage. That's a ratio. Tell you this about selectivity of this reaction. And they have to go write lab report on it. You don't. Okay. That does make sense? Okay. Now what? We'll do one more system. Okay. Same thing here. Not much different, more like an application. Okay. I'm gonna check that if you have been listening, if you are able to read the spin multiplicity. Okay. Let's summarize real quick. The regular coupling constant, regular mean they're next to each other like that. Okay, so we because 7 hertz. Okay, all right. For example, like this, they're about 7 hertz apart. Okay, now we have the alkene version. I mean alkene system. We have geminal, cis, and trans. Okay, small, medium, and large. That's all you need to know. All right. Now we're gonna move on to the double bond, but I'm going to attach an alkyl group right there. It's an alkyl group right there. Next to it, we have something a bit more complicated. Okay. Now let me explain. It's not that complicated. Okay. First thing first, go back to the J value, right? You see the number in front of J, 3, 2, 3, and 3. You see that right there? The number tells you how far apart the two protons are. How many bonds are between the two? For example, I'll go back one slide. Look at A and B. How many bonds are in between them? Can you count? Yo, count. How many bonds are between A and B? Count the bond. 3. This is trans, J3. See that? That's J3. Look at J2. Look at J2. Geminal. How many bonds are in between C and B? 2. That's J2. Okay. All right. So right now we're gonna move on to, we have J3, J4. We're gonna add J4 as well. Okay. Regular coupling constant about 7 hertz is J3. Usually J3 about 7 hertz. All right. This position is called an allylic position. Allylic position. The first one is an allylic position with the closest proton right there. You know, next to that proton. 3 bonds away, about 7 hertz, about 4 to 10, 7 hertz. When, all right, this is an allylic trans. Everyone follow me. How many bonds are between the red and the blue proton? Can you count bonds real quick? How many bonds? 4, J4. What happened when it's further away? Smaller coupling constant. Imagine this, if we have walkie-talkie, you're outside this room, I'm inside this room, we can talk, right? As long as we have the same the frequency, right? It's just frequency. Now, here's the thing. Same frequency, same walkie-talkie, but you walk all the way to the stadium and you try to talk to me. What would happen to the signal? It's weaker. Does that make sense? That's the weaker one. J4 is weak. Can you imagine J5? What would happen to J5? Usually they do not couple anymore that far. They won't couple anymore, too far. Okay? So that's why when you say J3, like it's about 7 hertz, they're next to each other. That's what we know. All right. So we have this is allylic position next to it, trans with it, cis with it. Look at the number, almost non-existing. Can you see that? That's why we don't talk about J5 in this course. That's not like very rare. J5 is so rare. Okay. So, all right, let's look at this compound. Now, I'm going to put the label on it, A, B, and C. Okay. So, who can couple HA? Who couple HA? For sure, this is a B. This is trans. Can you see that? For sure, this is a B. What? Anyone remember the range of coupling constant of trans? Right there, 12 to 18. You don't have to memorize it, but it's large. Make sense? It's large. So I'm going to give you, so let's say this large number. So about that. This comes from the instrument. Okay, so 15. All right, C and A. This is allylic position next to it. So we look at this right there. Allylic position next to it, 4 to 10. This is regular coupling constant. Again, do not memorize this number. The number like coupling, like a chemical ship, gotta come from the instrument. Does that make sense? Okay, I gotta give it to you on exam. Okay, so we found that it's gonna about 7. Yes, 3 bonds away, about 7. What is spin multiplicity of HA? Guess. Let's do this. If you have only HB, what would spin multiplicity of HA be? Guys, it's not that complicated. If you have only HB next to HA, what's spin multiplicity? It's a doublet, right? If you follow me, say I. Okay. So B make A doublet. Now look at C. C also split HA. If you have only C's, we have 3 C's. If you have only C, what would spin multiplicity of HA be? Quartet. Now put B and C together. 3C, 1B. What would happen to HA? We call this what? What? Doublet of quartet or quartet of doublet. Same thing. Okay. Let me show you what it look like. That guy. Okay. Let me show you how to draw the tree diagram. No, you tell me what to do. You tell me what to do. Okay. So now I'm going to show you tree diagram of HA. HA by itself is a singlet. Okay. So who split what? Who should we split HA first? Let's B. How far? Tell me how far. How far? 15. I'm going to go 7.5 to the left, 7.5 to the right. You get a doublet. You see that? What else should I do? HC, how many times? 3 times. Each time, how far apart? 7 apart. So that's 7 apart. We do first HC, second HC, and then third HC. Okay? That's like you have that. Then you go link that you get 2 quartet. You know? Quartet or triplet. And you're gonna go like 1 to 1, 1 to 2 to 1, 1 to 3. It's the same thing. But you see it right there. Okay. Let's try one more time. Look at HB. Look at HB. What's spin multiplicity of HB? Guess. HA and HB, if B couple A also couple B with the same number. Does that make sense? Okay, so HB is a doublet by HA. HA make HB a doublet. Now let's assume HC split HB too. Very small. Okay, look right here. This is allylic position and cis. We look for an allylic position and cis. Look at the number J4. So small. See that? Most of the time they don't split. Okay, let's assume they split today because we're practicing. All right, let's assume. Say what? I'll give you 1 hertz, just 1 hertz. So what's spin multiplicity of HBB? Doublet of quartet. Does that make sense? Okay, so it's a doublet of quartet, but it's you're gonna get a big doublet and a small teeny tiny quartet because it's only 1 hertz apart right there. All right. Look at the actual spectrum. That guy. Look at a big doublet. Can't even see the quartet in there. It's so small. Okay. All right. This one just help you be familiar with the coupling constant. Okay, just have you familiar with the number. Now what? Let's look at HC. I give you the coupling constant chart. Am I right? In the handout. All right, look at the chart. You're gonna look at the chart. Let's look at the chart. Okay. I'm trying to help you right here. So you're familiar with the number. Now, first thing first, look at the J3, C, and A. What does JCA mean? Who couples whom? A couples C. Okay, I'll look at the structure. A couples C. What's the relationship between A and C? Cis. What's the size of the church? Small, medium, or large? This is medium. That's a cis. Okay. Anyone know the if you look at the range? What's the range? 6 to 12. We found it 10. Okay, and that's what we found. That's from the instrument. This is 10. That's all you need to know. Okay. Next one. Look at C and B. Look at C and B. Okay. So B is with C. B right there. There's a C. Large, medium, or small? Small. Small. How small? About 2. In the what does it say in the chart for Gemini? 0 to 3. Very small. Very small. 0 means they don't couple. Okay. Last one we have C and D. C and D right there. C D is an allylic position. Allylic trans. Look for allylic trans for me. What's the number? It's small, right? Very small. Now, again, don't memorize the number. Let's do this. How far apart? How many bonds are between HD and C? There's a bond right there too. Count that one too. How many bonds? 4. J4. It's far, right? 4 is far. Can you guess what's the coupling constant be? Very small. This is really small. Only 1, or even less than 1. 0.5 to 2. You know? That's how you're familiar with it. You don't need to know exact number. Sometimes you don't even need to know the range. Okay. All right, one more time. Let's do one more time. Okay. Not A. This one. Look at B. Let's look at B together. Okay. So first one, J, B, and A. Okay. So A couple B. What's A? A right there. There's an A right there. Small, medium, or large? This is large. Why you say large? They're trans. Anyone know the range now? Trans. Yeah, 12 to 18. If you know, cool. If you don't know, it's fine. It's large. We found 16.8. You know? All right, next one, just C and B. C, what's a C and B right there? Small, medium, or large? That's small. Okay, how small? We found like very small right there. Okay, and the last one, we have B and D right there. This is allylic cis. Okay, how many bonds apart? 1, 2, 3, 4. This is J4. Can you see that? Can you imagine this is going to be very small? Yeah, how small? That's a 1. Very small right there.
If it didn't couple, would it just be double?
All right, it double quartet. If the quartet doesn't couple, it's just a doublet. Okay. All right, we're done today, guys. I'll see you after the summer break. Stay safe. All right.